Okay, welcome back everyone. So in this next example of conservation of momentum, we're going to be looking at an inelastic collision in two dimensions. So just as a reminder, inelastic means that some kinetic energy is lost, so the change is not equal to zero, but because momentum is conserved, we can still say that the change in momentum is zero. So it works pretty much the same as what we've seen in the past, but let's look at number 90 on page 213. So the setup for this is that two objects approach each other. So there's kind of a coordinate axis. Okay, so this object has a mass of m and a velocity of v, and they give us m is 2.0 kilograms and v is 3.0 meters per second. We'll call this the x direction and the y direction. Then we have a larger object, which is big M, traveling with the velocity of big V, and they tell us big M is 4.0 kilograms and big V is 5.0 meters per second. So this is a picture of the before, and then if I do it in a different color, what happens is they collide at the origin and they kind of stick together. Okay, so you have m and little m, and they move off with a speed of, well, we don't know. We'll call that v final. Okay, and so it's an inelastic collision, and we need to determine the components of the velocity. So we want to find vx final and vy final. And then we also need to determine the angle. Okay, so here's where that table that I showed you in a previous video for the momentum of a system, here's where that comes in handy. So what we're going to do is we're going to set up a table showing the momentum of the system. So we'll have the x direction, the y direction. We're going to have the little mass, little m, and the big mass, big M, and looks like the first object is going entirely in the x direction, so it has a momentum of mv, so this is a momentum table. So that's going to be 2 times 3 or 6, okay, and big M is not moving in the x direction. It has a y momentum of big M times big V, which is 20. And so if we add up our totals, we're going to have 6 kilogram meters per second and 20 kilogram meters per second. And remember what we did with this. We took this and we put them into a triangle. And so what we can do is we can find the hypotenuse, that is the total momentum initial of the system. And I actually didn't calculate the numbers for this because, well, you'll see in just a moment. This 6 represents the initial momentum of the system in the x direction, and this 20 represents the initial momentum of the system in the y direction. And what we know from conservation of momentum is that the initial momentum in the x direction is equal to the final momentum in the x direction, and if the initial momentum is 6, well, that's just equal to the final momentum. But now we have to be careful because the final momentum is the mass of the entire system times v final in the x direction. And it turns out that looking at things here, the mass of the entire system is 2 plus 4, and this tells us that v final in the x direction is going to be 1 meter per second. Likewise, we can say that momentum initial in the y direction is equal to momentum final in the y direction, so 20 is equal to 6 vy final. And it turns out that vy final is going to be 20 over 6, or 10 thirds, meters per second. And so there are the answers that we need for part A, the final velocities in each direction. Now if we want to find the angle, we know that we have 1 in the x direction and about 10/3 in the y direction. And we can find that that angle using inverse tangent is 73.3 degrees. So there's our answer for part B. Okay, so this is really not too terrible for two-dimensional inelastic collisions, especially if the objects stick together. It's just like we practiced for one dimension. You put the masses together and you can go from there.